What is logistic regression? Logistic regression is a classification algorithm that models the probability of the output loss. So given a set of dependent variable, we determine the probability of its happening or not by logistic regression. So basically it is a classification algorithm and it can be used in binary or multinomial classification. It estimates relationship between a dependent variable, which is a target or label, and one or more independent variable, where dependent variable is categorical. So dependent variable has its own categories, and we have to determine which category the output falls in for a particular set of input. Logistic regression features. Using this algorithm expects a smooth linear relationship with predictors. So when the relationship with the predictors is linear for the dependent variable, we use this algorithm. And logistic regression is concerned with probability of a discrete outcome. So it is a basically classification algorithm. It is slightly less prone to overfitting. So overfitting generally happens very less in this case because it fits a shape. It might work better when less data is available. So logistic regression also works better as compared to other algorithms when less data is available because it fits a shape. Assumptions used in the case of logistic regression are: binary logistic regression requires the dependent variable to be binary. So the dependent variable has to be binary in case of binary regression, binary logistic regression that is. For a binary regression, the factor level 1 of the dependent variable should represent the desired outcome. So one value of the dependent variable implies that the variable is there. Only the meaningful variables should be included. So it is talking about the predictor variables. Only the those which are relevant to the model should be included in the model. The independent variables should be independent of each other. That is, the model should be having little or no multicollinearity. So it is specifying that the independent variables or the predictors should not be dependent on each other. That is, they should have little or no multicollinearity. Collinearity when is happens when one or the other predictor variables is dependent on other. So it should not happen. The independent variables are linearly related to the log odds. So basically there is a logarithmic function involved in logistic regression. So in this case, the independent variables are linearly related to the log odds. Logistic regression requires quite large sample sizes. Sometimes logistic regression requires large sample sizes. The dataset should be huge. The logistic regression is applied only when the dependent variable is a categorical attribute. So we apply logistic regression only when we want classification. For logistics regression use case, the diabetes dataset example. Consider y-axis to be true when person has diabetes and false when person has no diabetes, and x-axis is the feature which is the plasma glucose of that patient. In the case of linear regression, the output was given by this formula, which was a straight line on the input x feature, where y cap is the value predicted by the algorithm. So this will be a straight line, but it won't be able to determine if the patient has diabetes or not because it is a sequence value from here to here, and 1 is here and 0 is here, so it cannot differentiate between 1 and 0. So we transpose this linear regression into logistic regression with this formula: p is equal to 1 by 1 plus e to the power minus y cap, where y cap is this already. So this oddness is solved out as you can see in the coming slides. So p is equal to 1 by 1 plus e to the power minus y cap, where y cap or y hat is the uh, mx plus c from the linear regression output. So here p is the probability of the output variable, which should be equal to 1 by 1 plus e to power minus bracket mx plus c finally. So basically the curve is like this here. So the probability p of the dependent variable is this, which can then further be solved to write this equation. So this is the logistic versus linear regression comparison in this equation here. So comparison of linear probability model and logistic regression model is shown in this slide. You can see the logistic regression model in the blue line and linear probability model in the red line. So the red line is basically when we use regression, there is a continuous variable which is the dependent variable. It is a continuous in nature and can have a range of values, but if it is having discrete values such as a binary classification problem, then we use logistic regression model, which is given by the blue curve. So as you can see, there is a sharpness from here to here and contradictory to the red line. So thus the logistic regression model handles the classification problem better because it gives the probability from 0 to 1 inclusive. So that will be the nature of the model. Binary classification and multinomial classification are shown in this slide. So basically for binary classification using logistic regression, we use the sigmoidal function, which is given by this function here. And for multinomial classification using logistic regression, we use the softmax function, which is given as this. So for j is equal to 1 to k, we have rho of zj is equal to ezj e to power zj divided by summation k is equal to 1 to k e to power zk. So the bottom denominator is having all the exponents and the numerator is having the exponent for the current z. Z is the class, particular class or feature for which we are calculating the softmax function.